Okay, I'm back with another lesson. And this lesson for today is section 4-5 in your textbook. Is titled More Congruent Triangles. And we're going to add on to that list of shortcuts that we previously had. Remember, we had SSS, SAS, and ASA. Today I'm going to add on two more shortcuts. And the shortcuts, like the previous shortcuts here, really just involve three parts instead of the entire six parts, 3 sides, 3 angles. So it does cut everything in half. The difference being is that these tend to be, one of them at least is a theorem. The other one is technically a postulate, but can be a theorem depending on the situation. We'll just put it that way. One of our new shortcuts here then is on your list of theorems and postulates. It's theorem 4-5, but again, I don't want you to call it that. I want you to call it by its letter name again, and this one's called the AAS theorem. Technically, it is a theorem, which means we can prove this one. Okay, but by the lettering alone, AAS already suggests to you that this S is not an included side. Remember, if it is the included side, it would be the one in between. They've worded this so that the S is at the end, so it's not in between the angles, so it will not be the included side. So a problem like this, where we might use this shortcut, would look like this. Suppose I have a couple of triangles here that I want to show congruent. And like it says up here, suppose I have a couple of pairs of angles. Maybe this top angle here congruent to that top angle. Maybe this angle here congruent to that one. Now the side that I'm going to have this time is not going to be the included side. So the one not in between. Remember, the one in between would be the one that joins the two angles. So you have some options here. I could pick this side out here or this side down here. Neither of those are in between the angles or joining the angles. So on this problem, I'm just going to go ahead and pick this side and its corresponding side over there. Neither of those sides, as you can see, are in between the angles. That's how it gets this name, AAS, as you go around. We always traditionally put the S at the end, not at the beginning. Instead of calling it SAA, we always call it AAS. You just got to look at it backwards to get the letters right up here. Excuse me. Now, the reason this works is actually goes back to another theorem we had. I can't remember the theorem number, but we did have a theorem, if you look into all your old postulates and theorems, that was called the third angle theorem. Actually, I believe it was earlier in this chapter. Yeah, it was earlier in this chapter, actually, right before we went on this extended break, that we had that third angle theorem that said that if two angles between two triangles match, the third pair of angles have to match. So you can see then that this last angle here has to match this last angle here because all three, remember, are supposed to add up to 180. Okay, so if we include that last angle then, that would have to match by the third angle theorem. Now I hope you can see that we can use one of our old shortcuts now too. We can use ASA to prove the triangle is congruent, because now using this new angle, we have two angles and the side in between. ASA. Okay, so this theorem is proved using our old postulate of ASA. But rather than going through those steps every time and having to say we're using the third angle theorem that those match and then using ASA, they just created a new shortcut where you don't have to worry about any of that then. We're just going to call it AAS. So if you do have any two angles and a side not included, we could use that new shortcut AAS and add it to our list. So if we know that's true, that's enough to say then that the triangles are going to be congruent. All right, so there's one other shortcut, and our last shortcut is something that I'm stealing from chapter 5 and including it with this chapter. Chapter 5 is kind of a hodgepodge of all kinds of ideas, so I'm just stealing this idea out of there. And the reason it's in there is because this last shortcut is unique to right triangles. It only works for right triangles. Let me erase this so I can show you my last shortcut here. And in chapter 5, it's actually out of section 2 of chapter 5. And if you look it up, it's listed in there. It's a postulate 5-1. Postulate 5-1. But again, I don't want you to call it postulate 5-1. I'd rather you call it by its name. It's called the HL postulate. HL. Now, we use different lettering because of the special unique case here. Like I said, this only works for right triangles. So let's say I've got a couple of right triangles, and I'm trying to prove that the two of them are congruent. Now, the name itself does not already include the right angle. So if they're right triangles, we already know they have a matching right angle. So you might say in a sense here that it's kind of like HLA, you might say, where that angle there is the right angle. But again, we don't include that in the name. It's just understood since it's a right triangle. Now, in addition to that, though, we have the H and the L, which with a right triangle, you could probably figure out means hypotenuse. The H is the hypotenuse, which would be right here across from the right angle. See it? Across from the right angle. And a leg. L stands for a leg. You get to pick which leg. It could be this leg down at the bottom. It could be the one that's vertical here and here. No matter which one you pick, you'll notice that this is the one time if we were to spell it out using our old A and S letters, this spells a dirty word. Look at it. A, S, S, woo-oo. Okay, so don't do that. Don't call it donkey. Okay, don't call it ASS. I'm going to count it wrong on a test if you do that. Call it HL. Okay, call it HL. Because we do have the hypotenuse here. That's the H part. And we do have a leg. And it's understood to already have the right angle since it's a right triangle. So we're calling this HL. But if you have that, that's enough to prove triangles congruent. And again, it's unique to right triangles. The reason it works and the reason it's a postulate is because currently as it stands right now, I can't prove it. But if I were to give you actual lengths here, maybe this is a length of 3 and this is a length of 3 and that's a length of 5 and that's a length of 5. If I were to give you actual measurements, you could actually prove this now. It goes from being a postulate to actually a theorem because we have the Pythagorean theorem, of course, that we could use. And in the Pythagorean theorem, we could find the last remaining side here by putting x squared plus 3 squared equals 5 squared. And then, of course, to solve for the x, you would subtract this over. So you'd have 5 squared minus 3 squared. And we would do the square root to get rid of the square. And when you do this, you could actually find the last side. In this case, the last remaining side would be a 4. So we would find that's 4. We could do the same here. Same procedure. Using x, we could do the Pythagorean theorem. Again, we could see this is a matching 4. And now that I have this last side the same on both of them, now do you see that HL is really just based on either side, side, side with all 3 sides, or even SAS using the right angle, SAS. So it's either or, either one of those. But again, all of this is not possible unless I actually know the length of that last remaining, of those two sides that are already marked congruent, so that I can find the last remaining side and now use one of our old methods. Okay, but even if I don't actually know these lengths, 3 and 5, it still works. Okay, I won't know these sides are congruent here though, but it still works. So we're just calling it a postulate then and saying that this still works here as long as you have a hypotenuse and a leg. That's enough to prove the triangle is congruent. So that extends our list now up to 5 ways to prove triangles congruent. Okay, so let's take a look now at some practice problems here, because that's all there really is to this lesson. And, oops, I better leave that up there. You'll want all these shortcuts handy. Okay, but we're going to figure out then which of these methods can we use to prove the triangle is congruent that I'm about to draw up here. So here's our first problem. Let's say I have, you may recall we did a problem like this earlier, and at the time we had said this was an impossible problem. Okay, but with our current knowledge, we can actually do this problem now. Because if you look at our picture, if that's a right angle, this is a right angle, and I see the two triangles share a side down the middle. So when I look at this one now, on each triangle pictured up here, if I were to cover this up, I've got two angles. Then I look at the side and I ask myself, is that side in between the angles or is it outside, not in between? And the one in between would be the one that joins the two angles. That does not join the two angles. So it's outside of these angles. It's not in between. So this would be our shortcut, our newer shortcut, AAS, that we just learned today. Okay, so that problem now becomes possible. Be careful if you were thinking, hey, it's got a right angle in it, it's a right triangle, it must be HL. Don't jump to that assumption, okay? Only right triangles can be used. This shortcut can only be used for right triangles, but just because it is a right triangle doesn't mean it'll be that shortcut. It kind of goes back to that idea of like, if it's a square, it's a rectangle as well, but not all rectangles are squares. Just because you see a right triangle doesn't mean it's HL, but it does have to be a right triangle to use HL. Let's see, how about this one? Let's say I've got a triangle here and another one there. And let's say this angle is congruent to that one, this is congruent to that one, and that side is congruent to that one. Kind of like our last problem, we have two angles and a side. See it? Two angles and a side. I just need to ask myself, is that side in between the angles or outside of the angles? Well, when I look at my picture, the side joining the two angles is the side they gave us, so that's the side in between. So on this one, this would be our old method of ASA, whereas this one's our new AAS. Okay, do you see the difference between these two? It's important that you be able to recognize that, because that's a common mistake people make. They're able to recognize in the picture two angles and a side on each of these, but you also need to be able to see this side's in between, so ASA, whereas the side in between here was not the one marked. This is a side not in between, so AAS. Okay, let's try a few more of these yet. Here's a third problem. Okay, looking at this problem, I've got these sides congruent, these sides congruent. I got a right angle here, and I hope you recognize I've got vertical angles. So if that's a right angle, this has to be a right angle. Okay, two sides in an angle. You got to ask yourself, is the angle in between the sides? Because if it is, then I can use SAS. So when I look at this one, there's my two sides. The angle in between those two sides would be the angle that's formed by them. So when this comes down, do you see there's the angle that's in between the sides? So that angle is not in between the sides. So if I put it outside, we spelled that bad word. Okay, the only time this ever works, though, as a bad word, is if it is a right triangle and we have the hypotenuse in the leg. Looking at this picture, across from the right angle is the hypotenuse. See it? And this side is a leg. So we don't call it donkey, you call it this instead. This one is HL. So don't give up on it just because it's spelled donkey, though. Look to see if you have a right triangle. Because on a right triangle, HL will spell donkey if you put it in the form of A and S with the letters. But call it HL. Okay, let's try another here. How about this one? Okay, on this one we know that's a right angle, that's a right angle. We're going to say this angle is congruent to that one. When I look at my picture, I also notice that the two triangles share a side, so I'm going to mark that congruent. That way now I can see in my picture I have three parts congruent. I've got a pair of angles here, a pair of angles there. So two pairs of angles and a side yet that matches between them. They share that side. Actually, it's a rotation, but is that side, though, in between or outside? You know, you got to ask yourself, because that makes the difference between ASA and AAS. So when I look at this one, there's my two angles. The side in between is the one that joins the angles. That's the side in between. So that is not the side in between. So I put it outside of it like this. And I realize then my shortcut is AAS on this one. Our new shortcut, one of our new shortcuts, that and HL. All right, so, be cautious, especially between these two right here. A lot of people get these confused. It's all a matter of whether the side's in between or not. And then remember that HL is the one time that it will spell donkey, but it has to be a right triangle to do that. And make sure you have then, of course, the hypotenuse and leg for that. Okay? So I think that's enough of those for practice. I want to finish with some proofs yet here, because we're going to do some more of those in this section as well. Okay, so I got some practice proofs here that we could do together. We'll start with this one. Given. And I thought we'd try one here that in the given they give you some parallel lines. That way you know what to do with the parallel lines if you come across those. I can't remember if I already gave you some of those in the previous section already or not, but in case you do run into any more of those, now you'll know what to do. On this problem then, we're trying to prove that BC is congruent to EC, and of course we need a picture to go along with all this. So our picture looks like this. And off to the side here again, I'm just going to put that list up here again of all our shortcuts on how to prove a triangle congruent. We had SSS, SAS, ASA. Those were the first three we learned. The new ones today, AAS and HL. And remember, these can be confusing. This one is based on donkey. So I'll just put a little star by that one. That's the rare occasion where you can get away with spelling donkey, but you still got to call it HL. All right, here we go. Step one, we just got to copy down our givens. So AB is parallel to DE, and AB is also congruent to DE. Don't assume those always go hand in hand, by the way. Just because they're parallel doesn't mean they have to be congruent. It just so happen on this problem they are. We put down that first step is given. All right, now in your 10 Commandments of proofs, there is a hint about the parallel lines. One of our commandments says that if you have parallel lines, you should be thinking about all those angle relationships that we learned about back in chapter 3. That included, remember, there was like corresponding angles, alternate interior angles, alternate exterior angles, and even same side interiors that are supplementary. But most of them were congruent pairs, right? And on your 10 Commandments, it should even say that most of the time on these problems, it's alternate interior angles that it turns out to be the case. Corresponding is a little more rare, as well as alternate exterior on these problems. But alternate interiors, believe it or not, occur quite a bit. So I think I put something on there like 90-some% of the time, it's alternate interiors. So if you look at our picture here, the parallel lines that they talked about were AB and DE. So I've got those highlighted here in pink. So if those are parallel, do you see that we can use a couple of different transversals here? So if I look at, for example, this transversal, now I can show then that the angles here and here that make up that Z shape, see it? Those angles are alternate interior angles, like I just mentioned, and they would have to be congruent. So I'm going to list that in my proof here. I'm going to mention that angle BAC is congruent to angle, and BAC, you see it, BAC, is congruent to this angle, EDC. How did I know? Remember, it was based on the parallel lines. And remember, in that chapter, we had different postulates and theorems that stated that these things are going to be congruent. And the alternate interior angle one is literally just called the alternate interior angles theorem. So if you want to put that, you can. The alternate interior angles theorem. It is a theorem, though. Don't just say because they're alternate interiors. Because if the lines weren't parallel, if they were going at a weird angle, these wouldn't match anymore. So it is part of a theorem. The theorem, by the way, is Theorem 3.1, if I remember correctly on the numbers. Theorem 3.1 is the one that says if lines are parallel, then the alternate interior angles will be congruent. By the way, that's not the only pair that you could name in this case. Okay, there is another pair. Oh, and before I get too much further, I'm also going to mark in our other given here, A, B, and D, E are congruent. So these are congruent. All right, now the other pair of alternate interiors would just be if you look at it a different way now. Instead of using this transversal, what if we looked at it with the other transversal going this way? You see it makes another Z shape where it goes down, up, and then back down. making that Z shape that has then some congruent angles again. Another pair of alternate interiors going like this. It might be a little bit smaller angle though. It's not necessarily the same as the last one. So we're going to mark it with a double arc. But we could list it as well in the same step because it's got the same reason. It's still alternate interior angles. So I'm just going to go ahead and list that second pair here as well. This time it would be called ABC because that angle, as you can see, is centered here at B. Centered right there, see, at B. And then they got a second angle over here that we're going to call DEC. Be really careful. See how the letters are just jumbled a little bit? So that's easy to mess up. So be really careful. All right, but as you can see, that gives me now 1, 2, 3 pairs of parts congruent between the triangles. Okay, and I've got it listed here in my proof as well. See, there's a pair of parts congruent, and then we had both of these pairs of angles. So once 3 parts are congruent, chances are you'll be able to use one of our shortcuts that also use 3 parts. So at this point, you could simply say that the triangles are congruent now. Now be careful, these said angle. See how this says triangle. So I'm just going to steal the lettering up here though. You know, the first triangle I'm going to call BAC, and then the other one would be EDC. But those 2 triangles are congruent. Not angles, but triangles. How do I know? Look at the picture. The picture gives away which type of shortcut you should be using. I've got 2 angles and a side. Is the side in between? Yes, it is. See how it's the one joining the 2 angles? So that is the side in between. So I write it like this with the side in between, ASA. So it's our old method, ASA. Okay, once you prove the triangles congruent, now you could go on and do what they wanted you to do all along. See how they wanted you to show these parts congruent, these sides? So you could do a follow-up at this point and say BC is congruent to EC. And do you remember the reason? Whenever you're trying to prove parts congruent, after you've proved triangles congruent, of course, you could then use the reason CPCTC. Corresponding parts of congruent triangles are congruent. But you can't use it until you show you have the congruent triangles like we did in the previous step. So there you have it. There's the proof of that one, which, by the way, does have an optional way you could do it. I don't know if anybody happened to notice this in our picture, but instead of naming the second pair of alternate interior angles, you could do this as an option. You might have noticed that, I'm going to erase that too here. You might have noticed that you've got a pair of vertical angles in this picture as well. So you always had the option of using it instead. And if you use those vertical angles, you would have made that your third step right here. You would have said that angle ACB is congruent to angle DCE. The 2 vertical angles at C. And you would say, okay, your reason would have been because vertical angles are congruent. Remember, that's at theorem 2.7 that we had way back in chapter 2. Okay, now the method would change as well. Now, do you see it's no longer ASA? Now, when you look at your picture, you've got 2 angles and a side, but this side is not the included side. Remember, the side that joins the 2 angles would be the one in between, and that's not in between. So now our shortcut instead of ASA would be AAS. And it would be our 4th step here. But then you still would follow up with CPCTC. So that would be a fifth step. So it drags it out maybe one more step just because you can't merge these into one step like we did earlier. And it also changes the method. Instead of ASA, you could use AAS, our newer shortcut. But notice, again, those two are closely related. So it's no surprise that there's an alternate way to do that that uses either method. All right. Let's try one more proof just to make sure you're catching on to these. And keep in mind, just like on that last problem, if you're ever given parallel lines and you're given, okay, I want you thinking that's going to lead to congruent angles. In fact, most of the time it's alternate interior angles. Okay, but let's try this proof next. I got one more proof after this as well. Can't do enough proofs. Practice makes perfect. So on this one, we're going to have AD bisects angle CAB. We're going to have angle C be congruent to angle B. And we're going to prove that triangle CAD is congruent to triangle BAD. CAD to bad. Our picture looks like this. And there's A, this is D here, a C here, and a B here. Step one, restate our given. AD bisects angle CAB. Angle C is congruent to angle B. It's always given. All right. One of our givens already just flat out gives us some congruent parts, gives us a pair of angles that are congruent. So I'm going to go ahead and mark that on my drawing. That's an easy thing to mark, and it gives me one pair of parts congruent already. We just need two more to prove triangles congruent. The other given here uses the word bisects in the 10 Commandments of proofs. When you hear bisect, you should be thinking that means it's going to cut it into two equal parts. What is it cutting into two equal parts? It's cutting that into two equal parts. This one is the bisector. It's doing the cutting. But what we care about more is who got cut in half. In this case, it's an angle. Angle CAB got cut in half. Looking at our picture, CAB is that overall angle at the top there. So the two halves of it would be split right there at the top at angle A. So that's going to be our step 2 over here. We're going to state that both of these angle A's at the top are congruent. Don't just call it angle A. You got to use 3 letters. You know, this angle A is CAD. And the other angle A would be called BAD. The reason that we put down over here, well, they use the word bisect, so we're going to use its definition. So we're using definition of a bisector. You could even get specific and say angle bisector if you'd like. Looking at my picture, that gives me 2 congruent angles so far. And I've used up all my givens. So there must be something else if I look back at the picture that I can mark congruent. And remember, in our 10 Commandments, it says to always keep an eye out for if the triangles share a side. So I can take that side AD and say that AD is congruent to itself. AD is congruent to AD. Okay, so anytime they share a side, that's what you do. You put it congruent to itself over here, and it always has the same reason as well. And it's that property we talked about. When we say anything equals itself, we're using the reflexive property. Just like when you look in a mirror, you see your reflection. That gives me 3 pairs of parts. That's usually enough to prove that the triangles are congruent. So at this point, I'm now going to say that this triangle is congruent to its reflection over here. So I'm going to say CAD is congruent to BAD, which, by the way, is what we're trying to prove. Do you see the reason? The picture gives it away. 2 angles and a side. Just ask yourself, is that side in between the angles or is it outside? Because if it's in between, it's ASA. If it's outside of the angles, it's AAS. The side that joins the angles is the one in between. That is not the one in between. So it would be AAS, the side that's not in between. And that means we're done on this proof because all we had to do was prove the triangle is congruent. If there were parts here that we had to prove congruent, then you'd have a follow-up step that would say CP, CTC for the reason. But on this one, we don't. Okay, I want to try one more. And I want to use one that involves our other shortcut that I haven't used yet in a proof, HL. So let's try one of those. Now, I kind of gave away already then that it's going to use that new shortcut. Okay, but normally they're not going to give you that hint, you know. So on this one, our given is that BD is perpendicular to BC. BD is also perpendicular to AD. And finally, one other given, AB is congruent to CD. And in the end, we're going to prove that angle A is congruent to angle C. Okay, here's our picture that we're using for this one. My markers are getting a little weak here. There we go. That looks better. And let's see. This is A. Here's B. C here. D here. Copy our given. So we'd say BD is perpendicular to BC. BD is perpendicular to AD. And finally, AB is congruent to CD. Well, that is given. Okay, so if all of that is given, then I would take any givens that you have, like this one right here, that automatically just tell you right away that you have some congruent parts. I would mark those off. So AB and CD are congruent. So there's one pair of parts congruent. But our shortcuts require 3. Both of these ideas both use the same symbol, the perpendicular symbol, which tells me then we must have some right angles. So if BD is perpendicular to BC, BD to BC, then I know I've got a right angle there. And if BD is also perpendicular to AD, BD to AD, then I've got a right angle there as well. So I need to state that, though, in my proof that I knew those were right angles. And if you remember right, when we did one of these earlier, the perpendicular part of this is going to have 2 follow-up steps, not just one. You know, our first step is going to be simply to state that angles CBD, and ADB are right angles. We got to kind of do it in stages. So we're going from saying they're perpendicular to saying they're right angles. The reason? Well, we knew it was true because of the perpendicular part. So we're simply using the definition of what it means to be perpendicular. But we're not done with this idea because we need to state some congruent parts. So this has one more follow-up step where instead of just saying they're right angles, we're going to write down that those same two angles, CBD and ADB, are congruent. And if you remember on that previous proof that we did together, the reason for that step would be because they're right angles. Don't say definition of right angles. It actually was a theorem we had that said all right angles are congruent. All right angles are congruent. Again, it was way back in chapter 2, and I think it was theorem 2.6, but don't quote me on that. All right, so that one finally came to an end, a dead end, you know, but it did give us two parts so far. We had the given sides congruent, and now the right angles that are congruent. But if I don't have any more givens to use, now I got to look to my picture to see if I can't figure out one more pair of parts, because all our shortcuts require 3. And if I look at my picture here, I notice that the two triangles share this side right down the middle. That side BD. So we can state that BD is congruent to itself. They share it, right? BD is congruent to BD. You remember our reason? This is always an easy step in a proof. If you see they share a side, you say it equals itself using the reflexive property. Like seeing your reflection in the mirror, they're a match. Technically in the textbook, by the way, they'll write this step as BD is congruent to DB. They'll write the second one backwards. And the only reason they're doing that, you see it's a rotation. So if I read this one as BD, when I rotate it around, it would then be called DB. So they like to write that backwards like that. I don't care though. If you just want to write it forwards both ways, BD, BD, that's fine. You know, it's just a technicality. All right, but that gives us enough now to prove the triangle's congruent, because I see I've got 1, 2, 3 parts congruent. I have it in my proof as well. 1, 2, 3 parts congruent. So all I have to do is determine which shortcut. When I look at my picture, remember that gives it away. But when I look at my picture, I notice I've got two sides. And normally I would need my angle that I have here to be in between, you know, SAS. But when I look at my picture, the angle that would be in between these two sides would be the angle formed by those two sides. It'd be up here at the top. So this is not the angle in between the sides. This angle is down here away from that. And we can't spell donkey, remember, but there is an exception. If it's a right triangle, the one that spells donkey is HL, and sure enough, look, we have a right angle, so that's the missing letter that you don't see in HL. That right angle is understood to be there. And then the H stands for hypotenuse. Well, across from the right angle is the hypotenuse. And L stands for leg. Well, that's a leg. That's not the hypotenuse, see? And on both cases, we have that hypotenuse and a leg. So, yeah, we're not going to call it donkey, but we are going to call it HL, that we could use to prove that the triangles are congruent. So I can state that triangle ADB is congruent to triangle CBD by HL. We're not done though, because look, we had to prove some parts congruent. But once the triangles are congruent, all of their corresponding parts match, including this pair of angles. It's one of the last pair of angles we don't have. See that? The A and the C. So we can state then, as a final step, step number 6, that angle A is in fact congruent to angle C. And do you remember the reason? After you prove triangles congruent, now remember it's fair game that you could use CPCTC. Okay, that's what we always use to prove parts congruent, but you can't use it to prove parts congruent until you first show you have congruent triangles, which we did in the previous step 5. So there you have it, a proof that uses even HL, one of our newest shortcuts as well. Okay, so if you ever see any right triangles involved, keep that in the back of your mind. HL might be one of our newer shortcuts that you can use. And it will spell donkey, though, if you use the old lettering system of A's and S's for angles and sides. This should be enough to equip you to do your homework here for section 4 or 5. So I'm going to call it quits on this video.